In this video, we're going to go through an example on determining both bending stress and combine bending and axial stress for a T-section. So this is, for our examples, the first unsymmetric section that we've seen, so we'll get to have a look at how that influences the bending stress, as well as we can have a look at how do we combine both bending stress and axial stress. So before we get started, let's just sort of go through what the question brief is asking us. So for part A, we just simply need to determine the bending stress if we have a 3 kilonewton meter moment applied to the section as shown. And so just a little bit of notation here. Whenever you see this double arrow, that means that there's a moment which is following the right-hand rule. So you take your thumb in the direction of the moment, and then your fingers curl in the direction that the moment is being applied. And so for this 3 kilonewton meter moment, it's going to mean that the top of this beam is in compression. So think about, if we were to take our hands like this, it'd be sort of in compression there. And in fact, let me just grab our little foam beam, thumb up here, and fingers curling over. So again, that's just a moment of sort of notation to be aware of. And so that's a pretty straightforward T-section, 40 millimeter width at the top flange. Both the flange and the web are 10 millimeters thick, and the web is 60 millimeters tall with a full section depth of 70 millimeters. So that's part A, is just simply to work out what the bending stress is. Part B is to determine what the overall stress distribution is when we have both this 3 kilonewton meter moment applied as well as a 15 kilonewton compression load applied. So that's what we're going to be looking at in this video. Let's get stuck in and sort of start working on part A. So the first thing that we need to know, if we're going to work out anything in terms of our moments of inertia, is what our centroid location is, because we're going to use the parallel axis theorem. We need to know the distance between each of the pieces to the centroid, and so with that, then we can just go ahead and work through what our capacities are. So we're going to find our centroid from point O, where y bar is going to come from the bottom of the section. And again, we could define it from the top as sort of arbitrary, but for this one, we're just going to go from the bottom. So to get started there, let's work out what our moment of inertia y bar, not our centroid location y bar is. And so that's going to be the sum of the areas multiplied by their distance to your reference point over the sum of the areas. And so if we have our top flange, well, that is simply going to be 10 millimeters thick times 40 millimeters wide. That's our area, times 60 plus half the distance for this rectangle is 5, so 65 millimeters. And then we're going to add 10 millimeters by 60 millimeters, 10 times 60. And then obviously its centroidal distance is half of 60, so that's 30 millimeters from the bottom. And then we will divide all of this by the total area, which is going to be 10 times 40 plus 10 times 60. And if we crank through all of this number, all this arithmetic, we get our y bar equals 44 millimeters from the bottom. There we go. Now, if we have y bar, well, that means that we can work out I, and so we're going to use the parallel axis theorem. So I is simply going to be the sum of the moments of inertia about their own centroids of each little piece, plus the area of each little piece, multiplied by the distance of the centroid of that piece to the centroid of the entire section, and that distance squared. So I is going to be equal to the moment of inertia of the flange plus the area of the flange multiplied by the distance of the flange to the centroid of the entire section squared, plus the moment of inertia of the web, plus the area of the web, times the distance from the web centroid to the centroid of the entire section squared. All right, well, we've got kind of everything laid out here. Let's just go through and work through some numbers. So the moment of inertia of the flange is going to be 1 over 12. Base of 40 times a height cubed of 10, so it's going to be 40 times 10 to the third, plus area of the flange is 40 times 10. And then the distance, well, we know that its centroid is located 65 up from O, and the whole y bar is 44 millimeters up from O, so we can just do 65 minus 44, that distance squared, plus the moment of inertia of the web, 1/12 times 10 millimeters wide over 60 millimeters to the third, plus the area of the web is going to be 10 millimeters times 60, and then its distance will be, 44 millimeters minus the centroid of the web, which is at 30 millimeters up from O. So we just simply have 44 minus 30 squared. And if we take all of that bits and pieces and we chug through our arithmetic, we get that I equals 4.77 times 10 to the fifth millimeters to the fourth. So now we have our section properties. So we've got our, we know our applied moment, we know our section. If what we're trying to find is our bending stress, well, we have sigma equals my over I. So we can go ahead and try to work out what our bending stress is at various points in the cross section. So if we start with looking at the stress at the bottom of the section, we'll just go ahead and draw a picture here. So if this is our cross section, and we'll put some dimensions on it. So we know that this distance to our centroid is 44 millimeters from the bottom, and that's the location of our neutral axis. We've got 10 millimeter flange. 44 minus 60 is going to be 16. And so if what we're trying to work out is sigma equals my over I, the distance at the bottom of the cross section to our centroid, y, is simply going to be equal to 44 millimeters. We know m equals 3 kilonewton meters because that was given to us, and we know I, so we can sort of work out what our bending stress is directly. So our stress is going to equal 3 kilonewtons per meter times 1,000 newtons per kilonewton times 1,000 millimeters per meter times 44 millimeters, and then I is 4.77 times 10 to the fifth. 4.77 times 10 to the fifth millimeters to the fourth. So our bending stress at the bottom is simply going to be 277 megapascals. So that's reasonably straightforward. Now let's go ahead and in fact, what I'll do is I'll just put in a little, sort of point of where we're looking. So this will be sigma bottom. All right. Now let's go ahead and work through what our stress is at the top of the section. So again, we'll just draw our cross section here, and we'll put some, cross-sectional properties on here. So our neutral axis, again, this is going to be 44 millimeters from the bottom, 10, 16, and we're trying to find sigma at the top. All right, so if we have sigma equals m times y over I, well, we want to find out what our y at the top is. So say y top equals, well, it's simply going to be our total depth of 70 millimeters minus y bar, which is 44 millimeters. So y top equals 26 millimeters. In fact, we'll come up here, we'll just label this y bottom. All right, well, again, like what we had here, it's kind of just a plug and chug operation. So we can go through our stress equals 3 kilonewton meters for a moment applied times 1,000 kilonewtons, 1,000 newtons per kilonewton times 1,000 millimeters per meter times 26 millimeters over 4.77 times 10 to the 5th millimeters to the 4th. And if we work through all of that arithmetic, we get sigma top equals 164 megapascals. So all of a sudden, we have something interesting which has come up. So this is the first time, as I said, that we've been working on an unsymmetric section. And so we are going to actually have different stresses at the top versus at the bottom, which, if upon inspection of our stress equation here, it should make sense, because if our neutral axis is shifted further from one end of the section than the other, well, the section it's shifted further away from will have more bending stress. And so it sort of should make sense. And so that means that, our maximum bending stress is going to occur at the bottom here, because it has a y distance of 44 millimeters away from the neutral axis, while the top has a distance of only 26. So that's sort of, we could stop there because we know that we have a linear stress distribution, but sometimes we need to find, the bending stress at a given point. This will become more apparent when we look at stress transformations and using, say, Moore's circle, but that's for a later video and later lecture. But, for the sake of sort of, working through it, and because we're already right here, let's go ahead and find, what our stress is at the interface between the web and the flange. So like I said, we don't necessarily need to do this because we know we have a linear stress distribution. But for some cases, we will need to do this to work out, what the combined bending and shear stress are. Just not in this case. So this is simply just a practice. And also just to sort of show you that this equation can be used for more than just the extreme fibers. So sigma top of web. Again, we're just going to go ahead and draw our little cross section here. And we're really trying to find sigma top of web. And again, we'll go ahead and just put some dimensions on here. So our neutral axis is up 44 millimeters from the bottom. We have, oops, sorry, I have this wrong. That's 16 that's 10. Or 16 millimeters to the interface between the flange and the web, and the flange is 10 millimeters wide. So here, if we want to work out, sigma equals my over I, our distance y to top of the web equals, right here, 16 millimeters. So we can just go ahead and plug this into our handy bending stress equation. So sigma equals our applied moment of 3 kilonewton meters. And then let's get that into newtons and millimeters just so that we can work and kick out a stress in MPa. So 1,000 newtons per kilonewton multiplied by 1,000 millimeters per meter times y top, which is 16 millimeters, all divided by our moment of inertia, which is 4.77 times 10 to the 5th millimeters to the 4th. And if we crank through all of that, we get our stress top of web is simply equal to 101 megapascal. All right, well, that's handy. Now, the next thing, so we've sort of worked out our stress at key locations, but what the question's asking for is to sort of determine the bending stress distribution. So we can take this and we can plot it up for an entire section. So if we just get ourselves onto a clean sheet of paper here, and we'll go ahead and draw up our cross section. All right, so we'll go ahead and just draw it with a straight edge just for the sake of nicety. So we're 40 millimeters wide, and we'll just come down here 10 and 10. And we know we've got we'll be centered within that. 10 millimeters either side. And then we'll come down 60 millimeters. And 60 millimeters. So that's our cross section drawn to scale. And we know that our neutral axis is located 44 millimeters up, so let's just locate that right there. So that's our centroid. And this is going to be our location of our neutral axis, so we can just sort of take that across. And let's just go ahead and put in our sort of vertical line for our stress distribution. So we know that we're going to be in compression on the top and in tension down below. So we're going to have some tension and some compression. All right, so that just sort of gets us located. Now let's just work out what our values are. So our compression at the top is 164 megapascals. So let's just go ahead and draw that out. We'll try to draw it somewhat to scale. So let's see. We'll take that to about 1 millimeter equals 10 MPa. So this is going to be sigma top equal to 164 megapascals. Our stress at the bottom is going to be 277 megapascals. So go ahead and bring this over. So 277 megapascals, and then obviously we should link just directly through the neutral axis, pretty darn close given the fact that we're just sort of doing all of this with a ruler. And that's our stress distribution, and if we find, if we come right here, sigma top of web will equal 101 MPa, and sigma bottom equals 277 MPa. This is in tension, and this part is in compression. So that's it right there. That's just kind of all there is to it. And so we'll actually, in fact, go, if we look starting at 10 for our scale, look, it's actually about spot on, 101. So we'll just draw that across. And in fact, you know what? We'll just go ahead and transfer all of these lines over. And we'll even draw in what our applied moment was. Three kilonewton meters. All right, so yeah, that's our cross section. That's what our stress distribution is for that cross section. So that's now worked out, part A. And like I've drawn this cross section here as a just as a 2D image, but I also went ahead and did a render of it for sort of looking at what that stress distribution would be if we look at it in 3 dimensions. And one of the nice things about this is it sort of shows why we're going to have different stresses at the top and the bottom of the section. And remember that if we treat, these stresses as sort of a volume, and we have some effectively resultant tension stress and some resultant tension force and resultant tension compression force, well, our compression and our tension have to be equal to each other. So it means that the volume of this stress has to equal the volume of this stress. Because our stress is going to be dependent upon its distance away from the neutral axis, if we have a lot of material up at some distance away from the neutral axis, so in this case we've got a big flange up here, the stress is actually smaller. But in order for our compression volume to equal our tension volume, the stress has to be bigger. So hopefully that sort of 3-dimensional example will help sort of show why we will have this difference in our stress distribution. All right, so that is that's sort of our part A, which was simply determining what the bending stress distribution was of the cross section to this 3 kilonewton meter moment. Now part B is say that we still have this 3 kilonewton meter moment applied, but then we also have a 15 kilonewton force which is pushing in compression. So if we have our little beam, we've got our 15 kilonewton meter moment there, and then we're also compressing it. So we're compressing it 15 kilonewtons, and we're also bending. So what is that combined stress state? And so we'll go ahead and transfer over kind of what we already know. So if this is our previous stress state there, and we go ahead and we sort of take our cross section. So part B combined M equal 3 kilonewton meters and P equal 15 kilonewtons. So if we know, from part A that our stress distribution for bending was 277 on the bottom. And what did we draw? 164 on the top. With a neutral axis at 44 millimeters. So 277. And 164 in compression. And this is from a 3 kilonewton meter applied moment. So this is, bending portion. Our axial portion axial stress is simply going to be the applied load over the area. So all we have to work out is what the area of the cross section is. And so, again, we'll just sort of sketch our cross section here. Well, if this is 10 millimeters, that's 10 millimeters. This is 60, and this is 40. The area simply equals 40 times 10 plus 60 times 10. And if we add that together, we get that the area equals 1,000 millimeters squared. All right, so that's very good. So then all we have to do is, if we know that P equals 15 kilonewtons in compression, our axial stress is simply going to equal P over A equals 15 kilonewtons times, we get 1,000 newtons per kilonewton over an area of 1,000 millimeters squared. Our axial stress is going to equal 15 megapascals. And it's going to have a stress distribution. Again, we'll just sort of sketch it out here. Which is simply going to be constant over the entire cross section, just because we're pushing, in compression, and our axial load will be applied evenly across the cross section. 15 MPa in compression. All right, well, I guess sort of the last thing we have to do is just work out what the stress distribution is of these two added together. So in order to find out what this combined stress distribution is, we simply need to add the two stress distributions from bending and from axial together, and then we'll see sort of how all of this shifts. So let's go ahead and just sort of put down a nice clean sheet of paper to do that. And we'll just draw out our combined profile. All right, so this combined profile, again, we'll just go ahead and draw our cross section here, and it has a centroid, which is going to be 44 up. We have 44, 16, and 10, and we'll just draw ourselves some dashed lines coming across. So this is simply going to be our stress due to bending. And again, we'll sort of bring our neutral axis over. So our stress due to bending, which we already worked out, was 164 at the top and 277 at the bottom. And this is our bending stress, sigma bending. Then we just simply need to add in our compression stress. Of 15 MPa. And we just simply, from linear superposition, we can just add these two together. So what that's effectively going to do is going to shift our whole bending stress over towards the compression side by 15 megapascals. So our total stress distribution is going to be 164 plus 15. 164 plus 15 equal 179 megapascals in compression. And then our neutral axis will shift down slightly. And then we have our tension and our compression. And our tension will simply be 277 minus 15 equal to 262 MPa. So this is sigma axial, sigma total. And so the only thing we need to do is work out neutral axis combined. And because we've pushed we've added more compression to it, means this goes out because we've got a linear stress distribution. Means that our neutral axis has shifted down from 44 to something less. So to work that out, all we need to do is use similar triangles. So to find the neutral axis of the combined bending and axial stress, distribution, use similar triangles. So, we know what the distribution is here for our bending, and we know the sort of length there. It's a right triangle, so we can work out what this height is just from similar triangles. So, if we're to do that, we would have $277 and 44. We have Y combo and 262. So the ratio of those two will give us what the neutral axis is. So we'd have 44 over 277 equals Y over 262. Y equals 41.6 millimeters. So equals 41.6 millimeters. And that's really all there is to it. So, so now in that video, just as a quick recap, we were sort of able to go from working out what our bending stress is for a non-symmetric section. And then through that, we saw that we're going to have different stress at the bottom than we are at the top, because the bottom is just further away from the neutral axis. And then if we want to try to account for the combined bending and compression, so the combined bending and compression stresses, all we have to do is simply add those two stress distributions up. And then the only really sort of somewhat tricky bit is just working out what our neutral axis is. But because we've got linear stress distributions, we can use the principle of similar triangles to get us there. So I hope that you found that pretty straightforward and something which will be useful for you going forward. So with that, thanks for watching.